We've now reached part 8 of my lecture on parametric tests for comparing means, in which we're going to see what happens if we have more than 2 samples to compare. If we've got more than 2 samples, one way to deal with it will be to do multiple t-tests, where we consider only 2 samples at a time and perform a 2-sample t-test on each pair. But a more sophisticated way is to use analysis of variance, or ANOVA, which deals with all samples at once. These are still parametric tests, so they require quantitative data, and they assume that the data are approximately normally distributed. Multiple t-tests means we take the samples 2 at a time and do a t-test on each pair. So for example, if we got 3 groups, let's call them A, B and C, we could start by comparing group A with group B, and we might find that the difference wasn't significant. We might then compare group A with group C, and we might find that was significant with a p of less than 0.01, and when we compare group B with group C, we might also find that significant with a p of less than 0.05. So from those 3 results, we can easily see that group C is different to A and B, because A and B are not different from each other, but A differs from C and B differs from C. So that seems a fairly straightforward way of doing it with 3 groups, but if we get too many comparisons we have to be a bit careful, because if there were 7 groups we would do 21 paired comparisons. Not only would that be a bit tedious, but we'd get into a problem, because we're talking about significance at the 5% level, which is a 1 in 20 chance. So if we do 21 paired comparisons, then we expect 1 in 20 of those, or 1, to be significant at the p is 0.05 level, even if the null hypothesis is true. So by doing so many comparisons, we're quite likely to find 1 that is significant by chance. Therefore, if we're doing this, we should require a higher significance level and go to 1% or even lower in order to avoid finding paired comparisons by chance. A better way is to do an analysis of variance, known as ANOVA. This compares multiple groups all at once to test whether they could all come from populations with the same mean. Now, analysis of variance looks at contributions to the variance. First of all, there's the total variance due to differences between individual measurements and the overall mean. Then there is variance between groups, which is due to difference between the group mean and the overall mean, and the variance within groups, which is due to individual measurement error. So the analysis of variance will compare the variance between groups with the variance within groups. That gives a variance ratio, or an F statistic, and we'll talk more about the variance ratio in lecture 7. But for now, let's just consider the fact that this is all based on what is called summed squared deviations, or SS. Imagine we've got some data representing rows and columns, and we've got 3 columns of data and 4 rows representing some measurement, some arbitrary measurement which has these values. The columns might be individual groups, the rows might be different ways of processing data. We can calculate the mean of each row and the mean of each column, as well as the overall mean of all 12 measurements together. Then if we look at the contribution to sums of squares, the total sum squared is the sum of the squared deviations of all 12 cells from the overall mean of 11.5. So we take 11.5 from each of those measurements, sum the squared deviations, and that gives us 29. You can work it out for yourself if you want. Then there is something called the row sums of squares. This is the sum of the squared deviations that would be obtained if every cell was replaced by its row mean. So for example, if we look in the first column, we've got 11, 11, 12, 12. If we replaced those by their row mean, we'd get 11, 12, 12, 11. Now, in calculating the difference from the overall mean, we can see that 11 has a difference of minus 0.5, 12 has a difference of plus 0.5, 12 is plus 0.5, and 11 is minus 0.5. So if we square those deviations, minus 0.5 squared is 0.25, plus 0.5 squared is 0.25, and so on. Adding those four gives us a total of 1. That is what we would get if we substituted the row means for all of the first column. But there are 3 columns to do that in, so each column gives a contribution of 1, 3 columns gives a total contribution of 3. So the row sum of squares would be 3. If we do the same thing with columns, then the column sum of squared is the sum of the squared deviations that would be obtained if every cell was replaced by its column mean. And the column means are 11.5, 13 and 10, which differ from the overall mean of 11.5 by 0, plus 1.5 and minus 1.5. So when we squared those deviations, we'd get 0, 2.25 and 2.5. And if we add those up, that's a total of 4.5. Now, if we replace the first row with that, and the second, and the third, and the fourth, we'd obviously get a total 4 times of that. 4.5 times 4 is 18, so that's the column sum of squares. Finally, we have the residual sum of squares. That's what's left. We had a total of 29. We've already accounted for 3 by the rows, 18 for the columns, and that leaves 8 for the residual sum of squares that's left over. 29 minus 3 minus 18. Don't worry if that seems complicated. You don't have to work it out for yourself, but this is just an explanation of what these sums of the squares mean. Analysis of variance works like this. We've already seen the row mean and the column mean for these numbers. If you do an analysis of variance calculation, the analysis of variance gives all the parameters that we need. Here it's been calculated by Excel. It shows a sum of the squares for the rows of 3, which we've already calculated, and the number of degrees of freedom, which in this case is 3 because it's the number of rows minus 1. 4 rows minus 1 is 3. The sum of the squares for the columns we've already calculated is 18. There are 2 degrees of freedom because there are 3 columns. The error is what I call the residual sum of the squares. The total we've already calculated was 29, and that should be equal to the sum of the ones above it. 3 plus 18 plus 8 is 29. The total degrees of freedom is the number of rows times the number of columns. 3 times 4 is 12 minus 1, which is 11, and that should be equal to the sum of the degrees of freedom above it. 3 plus 2 plus 6. The mean square is defined as ms, which is the sum of the squares, ss, divided by the degrees of freedom. That's a bit like a variance. That's how we define variance, as the average square deviation. In this case, the mean square for the rows is 3 ss divided by 3 degrees of freedom, which is 1. The mean square for the columns is 18 divided by 2, which is 9. And for the error, 8 divided by 6, which is 1.33. Then we calculate the F ratio, which is the ratio of the mean square for the row or column divided by the residual sum of squares, what it calls the error sum of squares here. Deal with that more in lecture 7, where we talk about variances. But in this case, we get for the row, it's the mean square of 1 divided by the residual mean square of 1.33, which gives 0.75, and for the column it's a mean square of 9 divided by a residual of 1.33, which is 6.75. So those are the F ratios. The p-value is the probability of getting that from the F distribution. This is another distribution that we haven't talked about, but we'll talk about more in lecture 7. Then the F crit is the critical value that is needed to be reached for a significance level of 0.05. In this case, the F value for rows is 0.75, which hasn't reached the critical value of 4.76, but for columns the critical value is 5.14 and our value of 6.75 has exceeded that, so we have a significant result for columns. So P is 0.03 indicates that we have a significant result for the column effect but no significant effect for the rows. So there is a difference between columns, but there is no difference between rows. If we have a non-significant result, that means that the groups could all have the same mean. A significant result simply means the groups are not all compatible with the same mean. It doesn't tell us which group or groups are the odd one out. If we want to know which group is different, then we would have to try several t-tests between individual groups, or maybe if we suspect one group, we could repeat the analysis of variance with the suspected group omitted. An important thing about using analysis of variance is that it gives us an idea of the overall measurement error, because the residual mean square, or the error mean square as Excel calls it, gives a good estimate of the overall variance of the measurements. So if we take the square root of the residual mean square, that is an estimate of the standard error of the measurement. So that's a good way of determining the overall precision of all the measurements once you've taken account of any variations between rows and columns. There are three varieties of analysis of variance. One-way analysis of variance with replication, which is the multiple sample equivalent of the unpaired t-test. A two-way ANOVA without replication, which is the multiple sample equivalent of the paired t-test. And two-way analysis of variance with replication, which is the same but when we've got repeat measurements. That's what the replication means. All of these are available in Excel using the data analysis tool, as long as you've installed the analysis tool pack. If you're doing multiple unmatched samples, then you use the one-way analysis of variance with replication. The variation between groups, like between group A, B and C in this example, is what we're trying to test, and the variation within each group, like the 4 measurements within each group, are due to repeats. Those are just random measurements. It wouldn't matter which order they were done in, so they're just repeats of the same thing, which allows us to detect the precision of the measurement. The analysis of variance is going to test the variation between groups, which is what we're trying to see, using the variation within groups as a measure of the precision of the measurement. If you are looking at multiple matched samples, then you use a two-way ANOVA without replication, and the variation between groups, like the variation between columns in this example, is what we're testing for. And if we're assuming that the rows represent patients, which they very often are, then that is something that we need to allow for, because every patient is known to be different, just like when we're doing a paired t-test looking at weights of every patient. Here every patient is going to be different here, so we're treating this as a fixed effect, something that we expect to be different and we need to allow for. The analysis of variance will test the variation between groups after allowing for variation between patients to tell us whether there is a difference between the groups irrespective of any difference between patients. And if we do the same thing with repeats, then a two-way analysis of variance with replication, the variation between groups is the effect we're testing for. The variation between patients is a fixed effect that we expect to be there, and variation within each group is repeats, which are random and give us some idea of the precision of the measurement. The analysis of variance will test variation between groups after allowing for variation between patients, and as well as allowing for the precision of the measurements, it will also detect an interaction between patients and groups. So for example, group C might always give a larger answer for patient 1 and a smaller answer for patient 6. That's what we mean by an interaction between the group and the patient. The rows might not always be patients, it might be some other classification, but I've used patients as a convenient example. If you want to do these calculations online, then there are calculators at Vassar-Stats for doing one-way analysis of variance. Select independent samples, or two-way without replication, where you have to on their program to select one-way and then correlated samples, or two-way analysis of variance with replication for independent samples. Unfortunately, that particular calculator only allows a maximum of 5 groups, but if you want to do more than 5 groups, Excel can do it quite happily for you. So that's the end of this part of the lecture on comparing means.